So today we're going to dive into our Unit 4 review.
What time we go back?
So we're going to start our review packet here with factoring greatest common factors. So again, as with the past test, each page kind of has a theme. So we'll just jot things down as we go. There's not a whole lot here to say, though, about greatest common factors because they should be the thing we've been looking for almost all through this unit. And they are the largest thing that divides nicely out of all of our terms. And when it comes to the variables, obviously you can't take more than what the lowest amount is available. So things to think about as you go through it, I would suggest that making sure you write down your greatest common factor for each little division will help you avoid missing some of the little pieces because you're keeping track of coefficients, you're keeping track of variables, and each of those variables could have a variety of exponents. So organization, as usual, is key here. Starting off with this first one, 30a squared plus 10a. Right off the bat, hopefully we notice that this is in fact a binomial. So we only have two terms to satisfy. And I usually suggest starting with the coefficient. So 30 and 10 have a greatest common factor of 10. And then if I look at the variables, do they have any variables in common?
A.
An A, and at most, how many A's can I take from both?
One.
Only one. I'm assuming that's because the second term only has one to give. Is that correct?
Yeah.
Okay. So again, I know we are trying to jot down a little extra information here today, just to kind of help with the studying. So this is our greatest common factor. Notice that it is underneath every single term. Don't get lazy on me here. Write it under each one. It'll help you avoid losing it. But as we have in the past, write it to the side before you actually go through and divide. So I'm going to write 10a first and then start my parentheses. 30 divided by 10 gives me 3. A to the second divided by a gives me a. 10 divided by 10 gives me 1, and a divided by a is gone. There was an a there, we took it away. There's no more variables on the second term. Quick reminder, if you're wanting to do a quick mental check, just ask yourself, would I get back to the beginning if I were to then go back and distribute that 10a back into the parentheses? Because that's what we want to make sure still holds true. So greatest common factor on that one was 10a. We divided it out, set it to the side, and this is where we got. Number 2, a little bit busier. We now have a trinomial, so we have 3 terms to satisfy. But I would suggest, again, instead of trying to do it all at once, just look at similar pieces. And I always like to start with the coefficients. So I see a 20, a 5, and a 25. So they would have a greatest common factor of 5. Can't be any larger than 5 because 5 is 5's greatest factor. It's a weird sentence to say. Then I go through and hopefully you notice there are 2 different variables here. So I'll start with the A's. Do they all have at least an A?
Yeah.
Okay. So what's the most A's I can take away here?
Just 1.
Why just 1?
Because it's all that has one to give.
Which one? The third one?
Yeah.
So the third one only has 1 A to give. So that's the most it can give away. So that is just an A in our greatest common factor. What about the variable B?
Yeah, you can take 1B.
Just one of the B's away as well. So if you notice, the second term only has 1 B to give, but they all have at least 1. So looks like here that our greatest common factor is going to be 5AB. Again, you don't have to do this extra notation on the test tomorrow. This is just to help us remember if we were to go back and look at it again. So greatest common factor, 5AB. I'm going to write it down to the side before I go through and divide. 20 divided by 5 gives me, careful, 4.
Oh, sorry.
A to the third divided by A
Gives you 2A. or A to the second.
A to the second, because we're only taking one of them away. B to the second divided by B
Gives you B.
gives us just a B. So that's the first term divided. -5 divided by 5
-1.
is a -1. A to the second divided by A
A.
is just an A. B divided by B
Cancels.
is gone. There was one B there. We took it away. There's no more. That takes care of the second term. Third term, 25 divided by 5
5.
is 5. A divided by A
Cancels.
is gone. There was one there. We took it away. B to the third divided by B
B to the second.
is a B to the second. There was 3. We took away 1, which leaves us with 2. Just like that, greatest common factor is now to the side. This one is factored. Questions so far? Again, be careful. I know obviously we want to fly through this as fast as possible, but don't try to do everything all at once yet. Now, with lots of practice, you can look at this and do it probably more quickly. Some of you are getting really close to that point, but especially on test days, don't rush it. Take as long as you need. Number 3, another trinomial. So we have 3 terms to consider. Starting with the coefficients, I see 21, 6, and 3.
3.
So 3 would be their greatest common factor. Then I notice x's. Do they all have x?
Yeah.
What's the most x's we can take here?
4.
4. Okay. And is that because of the last term only has 4?
Yes.
Okay. But I notice there's a y in there on the second term. Can I take that out of each term?
No,
Why not?
because there's no other Y.
There's no other y's. They would all have to have at least one y to be able to take it from all of them. So it looks like our greatest common factor here is 3x to the 4th. So we'll set that aside before we divide. So 3x to the 4th. Then we go through 21 divided by 3
7.
gives me 7. X to the 6th divided by x to the 4th.
X to the second.
X to the second, because there were 6, we took 4 away. There's only 2 left. That takes care of the first term. Second term, 6 divided by 3
2.
gives me a 2. X to the 7th divided by x to the 4th
Third.
gives
3.
x to the 3rd. There's 3 left. What about that y?
You bring it down.
Bring it down. If you didn't do anything with it, if you didn't move it, didn't remove it, leave it with the term that was on. And then the last term here, -3 divided by 3
-1.
is a -1. X to the 4th divided by x to the 4th,
Cancels each other out.
gone. There were 4 there. We took 4 away. There's no more x's left over. So that one is factored. Yes, it got it.
Hey,
On our next one here, yes, it's multiple choice. Don't let that distract you too much. Sometimes we get so caught up in the possible answers, it influences our work. What I would suggest is just focus on what you know you want to do. So it is a trinomial. So we want to consider all 3 terms. Starting with the coefficients, I have 70, 21, and 14.
Seven.
7 would work. What about the variable? Can I take n out of every single one of them?
no.
No. So unfortunately, the last one has no variables to give. So as much as I'd like to try, I can't. So I would write the 7 to the side, which makes me suspect it's going to be B, but let's make sure. If I divide those out there, 70 divided by 7,
7,
oh,
10,
10. And since we're not taking any variables away, the variables actually stay exactly as is. 21 divided by 7 should give me
3,
3. That one still has an n. And then negative 14 divided by 7
-2.
should be a negative 2. So it would in fact be B. In fact, if you took some time to look at some of the other answers there, hopefully they each in their own way seem kind of nonsensical. Like how would you divide that to be that way? Like how would you divide 21 by 2 and get 10? Maybe if you were rushing, I don't know. All right, so the top 4 here, I'm gonna zoom out real quick. The top 4 here were all things greatest common factors. Now that doesn't mean we stop checking for greatest common factors through the rest of this review. Because remember, you always check for greatest common factors first, but these are the only 4 where you only have to check for a greatest common factor. The bottom 2 on this page is having us factor by grouping, which the reason why I put it on this page is because if you recall back when we learned greatest common factors and factoring by grouping, it really just had us using greatest common factors 3 times in the same problem. First in the 2 halves, and then for the binomial that we hopefully have in common when we go through this process. So when we think grouping, typically what we did was we cut it in half to give us our 2 groups. Because if you look at it, the odds of you finding a greatest common factor for all 4 terms is a lot less likely. The more terms you have, the harder it is to find a greatest common factor. So starting with this first one here, by grouping it, I'm going to cut it in half here. Notice I keep the signs with their terms, and I'm going to focus on the left-hand side first. So focusing on these 2 terms, if it helps, if you need to see that negative 1 that's hiding there, draw that in as well. What would be the greatest common factor on the left?
1,
1, because obviously factors of 1 only are 1. But do they have any variables in common?
x to the 2nd.
X to the 2nd. They both have at least 2 we can take away. So on the left side here, 1x to the 2nd is the greatest common factor. And as we divide it out, 2 divided by 1 gives me 2. X to the 3rd divided by x to the 2nd
X,
is just an x. Negative 1 divided by 1
-4,
is a negative 1. And x to the 2nd divided by x to the 2nd
cancels.
is gone. So the left side is factored for now. Then I move on to the right side. So I have 6x and -3. 3 would work for the coefficients. Can I take any variables away?
No,
So can't take any variables away because the last term there doesn't have any. So 3 would be my greatest common factor here. So I'll put a positive 3. Dividing it out, 6x divided by 3
2,
should give me a 2x, and -3 divided by 3
-1,
is -1. And why am I happy?
because they're all the same. The things in the first.
The things in the binomials in the parentheses are identical, not close. They are identical. So a little quick side note here, a little reminder. I'm happy when the binomials in the parentheses are identical. The reason why I'm happy is because that's going to allow me to take out a greatest common factor one more time. Because if you're imagining this as still two separate halves, those two separate halves share the greatest common factor, which in this case is the binomial 2x minus 1. So like with any greatest common factor, we write it under each part. So this is the two halves here. But before we divide, we set it aside. So the 2x minus 1 is still there. But when we go back to divide, all it does is it removes it from those two halves. And what we get in our final set of parentheses is whatever they leave behind. So in this case, we get a 1x squared plus 3. Which for some reason I don't have a solution line on mine, so I'll just box it in. So I'm happy when the binomials and the parentheses are identical. And in the event that they're not quite the same, that's when we usually go back and maybe readjust the little greatest common factors we took out of either half. Moving on to our second factor by grouping. Again, since I know it's asking me to do it by grouping, I'm just going to go ahead and split these again straight away. Starting on the left-hand side, what do you think the greatest common factor there would be?
5.
5 will take care of the coefficients. Any variables?
X to the second.
X to the second as well. They both have at least 2 x's to give. So 5x to the second is the greatest common factor on the left-hand side. And when I divide it out there, 20x to the third divided by 5x to the second
You get 4x.
should give us 4x. Negative 5x to the second divided by 5x to the second
-1.
should be just a -1. So we have a goal here. We're hoping that on the second half, we get a 4x minus 1. Now this one's a little bit odd because already I see a 4x and a 1, but their signs appear to be the wrong ones.
Divided by -1.
What does dividing by -1 do for me?
It'll give you a positive form or -1.
Absolutely. So the dividing by -1 will make the 4x positive and the 1 negative, just like we would like to see. But that means then that our greatest common factor there was a -1. That's important that we don't lose that. But as we divide it out, as Leanna said, we do get a 4x minus 1 again, which is what we like to see, because then we can wrap this one up by dividing that 4x minus 1 from these two halves. Just don't get lazy on me. 4x minus 1 is being divided from the two halves. That is our big greatest common factor there. Set it aside before you divide. But in this case, dividing a binomial by itself just eliminates them. And what you get in your second set of parentheses is what's left over. So in this case, my second set of parentheses is 5x squared minus 1. So greatest common factors, although technically is considered a simple version of factoring, can be applied at a more advanced level, and that's what allows us to factor by grouping. Any questions on this page? So moving on to the second page, factoring quadratic trinomials. So quadratic trinomials, we spent a day specifically on factoring these. Don't forget though, we don't stop checking for a greatest common factor first. But for factoring quadratic trinomials, I'll put this up here in the margin. This is where we used the asterisk method. So by quadratic trinomial, that usually means it's in descending order. If not, we make that happen. But very generically, it looks like ax squared plus bx plus c. And from that, using the asterisk method, which looks like this, we should be able to factor it into two separate binomials. I should notate this real quick. So again, this is, I think this was the same lesson I gave you, that factor pair list. That again is going to be a wonderful tool to have available. You're more than welcome to have that with you come test time tomorrow. No sense sitting there trying to come up with your own factor pair lists when I've provided you the first 100 already. So a lot of asterisk method on this one. And I do believe I was even nice enough, because I think I had a student in the past say, hey, can you give us the asterisks? And I'm pretty sure all the problems on the test tomorrow that require the asterisk method have an asterisk already provided for you. So think of it as a bonus reminder to say, ah, I know what to use here. All right. So our first one here, what do we always check for first? Greatest common factor. Not like terms. That was our thing we're doing last week. Now, is there a greatest common factor here other than 1? No. That coefficient of 1 kind of traps us with 1, and because they don't all have at least one of the same variable, there's not a greatest common factor here other than 1. So in that case, what's my A?
21.
Oop,
Or 1.
1. B
-10.
is a -10, and C
21.
is 21. So these are going to be the values we use in our asterisk method. So where's my spot here? I'll just write it down below. I'm going to draw in my asterisk. And we'll have A times C on top. So we're looking at 1 times 21, which is just 21. A on either side are 1s, B on the bottom, oops, is -10. So this is where I would grab the factor pair list, look at factors of 21, and try to find the pair that would somehow, maybe with a manipulation of signs, allow me to add them to equal -3 and 7. Now let's check that real quick. 3 times 7 does give me a 21. 3 plus 7.
-7.
-7. Good. Let's check that then. 3 times -7 is -21.
Could we do them both negative?
Let's see. -3 times -7.
Positive 21.
+21. -3 plus -7.
-10.
-10. So remember, there's no rule to say that they always have to be one sign or the other. Play with the signs until you get the outcome that you're looking for. So -3 times -7 gives us that positive 21. -3 plus -7 gives us the -10. And with those numbers in place, we now have the two pairs that are going to help us find our binomials. Now, do either of these two pairs simplify at all?
No.
No. And anytime you got 1s on top, they really can't get any more simpler. So we'll still have a 1 over -3 and a 1 with the -7. Bring back your variable, which this turn was the letter N. And then we write the top value in front of the bottom value for each. And that should be where we get our two binomials. In this case, 1n minus 3 and 1n minus 7. If you're putting the 1s in front of your n's still, that's fine too. I try to do it interchangeably. Number 2. What do we always check for first? Greatest common factor. You're thinking there's a 5? I would agree. I would agree that every one of these terms could be divided at most nicely by a 5. So it's really important we get that out of the way first. A little reminder here on the side. So we're going to set that aside. And when we divide it out, it looks like we're going to get a 1x squared plus 11x plus 10. And with that aside, now my A, B, and C are significantly smaller to then jump into the asterisk method. So what's my A now?
1.
Is 1, B
11.
is 11, C
10.
is 10. So with those values in place, jump into our asterisk. A times C on top, so we're looking at 1 times 10, which is 10. A on either side, so there goes my 1s. B on the bottom is 11. So factors of 10 that add to equal 11. 10 times 1. So 10 times 1 gives me 10. 10 plus 1 gives me 11. So straight away, we get our 2 pairs pretty quickly on this one. Do either of them simplify?
No.
No. Anytime you got those 1s there, they really, like I said on the last one, don't get much simpler. Much more simple. I don't know what the proper grammar is there. Bring back your variable, which is the letter x on this one, and we should get the 2 binomials, 1x plus 10 and 1x plus 1. Did I forget anything?
The 5.
The greatest common factor of 5. Don't lose it, because without it, you can't get all the way back to the original problem. So you set it aside early on. Don't forget to bring it back for your final solution. Okay. Number 3, any greatest common factor here? No, I don't think so. 23 is a prime number. So unless they all have factors of 23, which is impossible because they're both smaller than 23, there's no greatest common factor here other than 1. So I jump into my asterisk. What's my A?
10.
A is 10. B
-23.
is negative 23. And C
9.
is a 9. So ready for the asterisk. So A times C on top, I'm looking at 10 times 9, which gives me 90. A on either side, there goes our 10s. B on the bottom is a negative 23. So I want 2 numbers that multiply to equal 90, but at the same time add to equal negative 23. I think 90 has a longer list, so this may take just a brief moment.
Eighteen times 5.
18 and 5. Okay, so 18 times 5 is 90. 18 plus 5 gives me a positive 23.
I do both of them negative.
Both negative again. So that's good because negative times the negative still gives me that positive on top. But the negative plus the negative on the bottom is going to give me the negative 23 there. So I got my 2 pairs. Do either of them simplify?
Yes,
Which one?
the 10 and the -5.
10 and the -5.
Is it a house?
Ah, careful.
Well, no, you get 2 over 1.
Yep, if you divide a 5 out of each of those, you're gonna get a 2 over a -1. What about the other one?
Yeah,
I think you can divide a 2 out of both.
yeah.
If you divided a 2 out of 10 and 18, you get a 5 over a -9. So that looks a little bit better. Bring back my variable x. And it looks like we get the binomials 5x minus 9 and 2x minus 1. Just remember back to when I first showed you the asterisk, it's like, whoa, what is this weird thing? But with some practice, all of a sudden it just becomes very repetitive, which, yes, is a little bit boring, but at the same time, it's a little bit more comforting. Next one here, again, don't get distracted by the multiple choice. It could influence your decisions. Go with your instincts. What do we check for first?
You can take 2 out.
We can take a 2 out as a greatest common factor. Sounds good to me. So let's do that first. It's dividing a 2 out of each. Set it aside. 8x squared divided by 2 should give me 4x squared. -38x divided by 2 gives me a -19x. And -10 divided by 2
-5.
gives me a -5. With that out of the way, still need to factor a little bit further. What's my A?
4.
4. My B?
19.
-19. And my C?
-10.
Oop, oop, oop. We divided out of 2. We got a -5. So grabbing our asterisk here, A times C on top, we're looking at 4 times -5, which gives me a -20. A on either side gives me 4s. B on the bottom is a -19. So factors of -20 that also add to equal -19.
-1.
20 minus 1. I think you're close.
Well, could
Do you want the 1 to be negative? Is that what you're saying?
Yeah.
Well, let's check. 20 times a -1 would give us a -20. 20 plus a -1 would give me a positive 19.
So then the 20 is negative?
So you want to switch the signs?
Yes.
You don't want them both negative, right?
No.
Okay, so -20 times 1 is still -20. -20 plus 1 gets me that -19. Do either of these pairs simplify?
Yes.
Yeah.
Which
2 out of 20 and out of 4.
Ooh, you could take 2 out of the 4 and the 20, but there's a bigger one.
4.
You could take a 4 out of 4 and 20, which would give you a 1 over a -5. And I think the 4 over 1 stays the same. Bring back your variable x. And it looks like you get the binomials 1x minus 5 and 4x plus 1. Don't forget, though, we also had that greatest common factor. Now, remember, order of multiplication technically doesn't matter. So we want to find the one that has at least these 3 pieces to it. Maybe not necessarily in the same exact order. C is going to be the one that does it. So even though the 2 binomials are in reverse order there, they are still there. They are still being multiplied. That's what we're looking for. Number five. Number five is a little bit sneaky. It is asking us to find the equivalent expression. So in other words, factor it, find the binomials. But this one does have this extra statement that says select all that apply, which leads me to suspect that there may be more than one correct solution. So we want to be careful to make sure we look at them all once we get this one factored. Regardless, what do we always check for first? Not like terms.
Greatest common factor.
Greatest common factor. I don't think there is one other than one because of that one in the third term there. So what's my A?
7.
7. What's my B?
-8.
-8. And my C?
1.
+1. So then I come and set up the asterisk. A times C on top. So we're looking at 7 times 1, which is 7. A on either side, which are also 7s. B on the bottom, which is a -8. So two numbers that multiply to equal 7, but also add to equal -8.
1 and 7.
Well, yep, so 7 is prime, so our list is very short. So I'm thinking that it's really going to come down to the signs. Because right now, 1 plus 7 gives me a +8.
Both of them could be negative.
Both of them could be negative. That would still multiply to equal a +7. But now when you add them, you'll get that -8. Do either of these simplify?
Well, technically, you can take 7 from 7.
You could
So,
take
yeah.
7 from 7, so that would make that 1 over -1. 7 over -1 stays put though. Bring back our variable, which this time is the letter n. And it looks like we get the binomial 7n minus 1 times another binomial 1n minus 1. Well, right off the bat, I see A matches identically.
C,
C also works? Is it the
Yeah.
same two binomials?
they just flip-flop them.
So both would be correct. So long as you have those two exact binomials, regardless of the order that they're written in, you still have the right factored form. How do you guys feel about the asterisk method? So. If I gave you the template, if I gave you the factor pairs, Okay.
Sometimes I remember, forget which one was where.
so I will give you that template because if I was in your position, let's say I had to memorize something, I would grab a sticky note, I'd write the template and I'd stick it to the edge of my monitor. If I was using it regularly, I would stick it there. Now, would I eventually memorize it? Sure, which I've accidentally done now and using it so many times. But absolutely. I'm more interested in your application, not your memorization. Third page here. So this third one, I mentioned that it would come up, and I think I even said that there was a whole page dedicated to it in the lesson where we first introduced it. And that is factoring the difference of perfect squares. Now, this was the special case. I even threw some in on the assignment that went along with it. But let me jot in a few little, hopefully helpful pieces of information. First off, your perfect squares. They are listed on your factor pair list, but I'll give you the first, at least the first 10. And they are 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. I'll even give you a few bonus ones that aren't on your list. 121, 144, so on and so forth. And these values simply come from taking a number and squaring it. 1 squared is 1, 2 squared is 4, 3 squared is 9, so on and so forth.
Do you ever notice it's counting, like 1, 2, 3, 4? Like at the bottom numbers? So it's just count.
Oh, if you square them?
Yes.
And that's what I do in my head when I'm listing them out, so I don't accidentally skip over one. Technically, there are perfect squares that are between those. So technically, if I took 4.4 and squared it, I would get a decimal, but it would still technically be a perfect square of a decimal. But we don't muddle too much in those waters there. One additional thing I'm going to throw in there real quick, those are my perfect squares, is the little formula, which may have helped some of you, may have not. It's really maybe just the implementation is what helped. But the difference of perfect squares says that if you have an item being squared minus a second item being squared, that will immediately factor into two binomials where you take the first thing being squared plus the second thing being squared times the first thing being squared minus the second thing being squared. So really what it all boils down to is you need to figure out what is being squared to make that term. So jumping into the first one here. I already suspect it's a difference of perfect squares because 1, it's a binomial. 2, I see subtraction. 3, this is the one we really need to kind of consider more heavily. Are those perfect squares?
Yeah.
Sure. Those two values are on my list. So what I would ask myself is, what is being squared to make 25x squared?
5.
5 and
Oh, X.
and an x. So a 5 is being squared to make the 25, and the x is being squared, obviously, to make the x squared. So 5x is my first piece I'll need. What's being squared to make the 16?
4.
A 4. So 4 is the second piece I'll need. When I go to factor them, I'm just going to use those two pieces twice. 5x plus 4 and 5x minus 4. And it's factored. The hardest part is figuring out what's being squared. Second one, a little bit more challenging, only because some of the information seems to be hiding. But what is being squared to make m squared?
M.
Just an m. That one's not too bad. What's being squared to make 64?
8.
So although it doesn't seem like there's a number there, technically we could say that there was also a 1, because 1 squared is 1. But if you imagine that it's hiding the whole time, you can actually get away with not using it. What are my two binomials going to be?
M plus 8.
M plus 8. And the second one?
M minus 8.
M minus 8. Done. It's a really neat shortcut once you feel comfortable using it. It does kind of require you to know your perfect squares. Good news though is you can always check any number to see if it's a perfect square if you have a calculator handy. And I'll show you that here in one of the following ones. Moving on to the third one. What's being squared to make 8a squared?
15.
To make 8a?
Oh, 4. I'm dividing in my brain.
Okay.
Well, I took the greatest common factor out first.
So I didn't even have to, I'm glad you said that. What should we always be checking for, regardless of whether there is one or not?
Greatest common factor.
A greatest common factor. And that is especially important here because right now, 8 and 18 are not perfect squares. However, they do share the greatest common factor of 2. So if we divide that out, just like we do any other greatest common factor, set it aside before you divide. That binomial is going to turn into 4a squared minus 9. Now, those are perfect squares. What's being squared to make the 4a squared? 2 and a. And what's being squared to make the 9? A 3. So don't lose that greatest common factor. We'll come back and grab it later. But what two binomials should we get here?
2a plus 3.
2a plus 3 and
2a minus
2a minus 3. And because we had to set that greatest common factor aside, we just bring it on down. Because without it, we could only get as far back to 4a squared minus 9.
Can you show us how to check our answers on these?
You want to see how to check this one?
Yes.
Sure. So yeah, we'll do a quick check here on this one. That's a good question. Not required on the test, but if you're curious, you can do it. So what are your instincts telling you, Leanna? What would you do first if you were checking this? You want to use the box method on the binomials? We can do that.
Well,
And then use the greatest common factor later?
Yeah.
Sure. So to multiply two binomials together in the past, we set up a box. Apparently my iPad doesn't want to do a box, but we would set up a box to multiply those two binomials together. So 2 rows, 2 columns, 2a positive 3, 2a negative 3, and then we would fill in each row by multiply each row by each column. 2a times 2a would give me 4a to the second, because remember you're adding their exponents. Going to the right, 2a times negative 3, negative 6a. Going down to the second row, 3 times 2a, positive 6a, and 3 times negative 3, negative 9. And what we liked about the box was usually at this diagonal, we had like terms, but what do you notice these like terms are going to do?
Cancel each other out.
Cancel, because 6a plus a negative 6a is 0a, which is gone. So multiplying those two binomials together, I get 4a squared. The like terms cancel, so that leaves me with negative 9. Now I can't forget that I haven't used the greatest common factor yet, at which point I would do what?
Multiply.
Distribute, which is fancy multiplication. 2 times 4a squared would give me 8a squared. 2 times negative 9 would give me a negative 18. And just like that, we're right back to where we started. So you're more than welcome to check any of them that you want, because for the most part, most of these problems we've done both forwards and backwards, just not at the same time. It's a good question there. Not required, but a neat little exercise nonetheless. Moving on to the fourth one here. Now, this is where I told you, I can't give you a list of all the perfect squares because that list goes on forever. So obviously, I haven't told you whether or not 529 or 324 are perfect squares, but this is where I would grab the calculator and use the square root button to see what you get. What's being squared to make 529x squared?
23.
23. And the x. And what's being squared to make the 324? Gotta guess.
18.
I would say the 18. Now, the trick is making sure you get your signs right, because this one is multiple choice, and I see a bunch of 23s and 18s. So we want to make sure we get the pairing and the signs right. So if I was doing this one myself, I would say 23x plus 18, 23x. Oh. So if I was writing out these binomials, I'd have 23x plus 18, 23x minus 18. Which I don't see one exactly in that order, but Leanna is telling me that D does at least have those two binomials just in the reversed order. So D would be my answer there. So again, that square root function on your calculator can help you check to see whether or not a value is in fact a perfect square. Because if it is, and you take the square root of it, it's going to give you what was being squared to make it. Last one on this page here. It's worded a little bit differently, but if it's on the page with the difference of perfect squares, odds are we're finding the difference of perfect squares. But instead it says the area of a rectangle is represented by 100x squared minus 49y squared. What are the dimensions of the rectangle? Well, to find the area, it's really just length times width. So if I can find two things multiplied together to make this binomial, I would technically have the dimensions. And when I look at the expression I'm given, I notice that this looks a lot like a difference of perfect squares, to which I would then ask you, what is being squared to make 100x squared? 10x. And what is being squared to make 49y squared? 7y. So with that reasoning, then I should be able to get the two binomials, 10x plus 7y and 10x minus 7y, which doesn't really matter which one's which one is which. One of them is length, one of them is width. So you found them. They don't look like dimensions that we typically use for finding areas of rectangles, but that's just because they're missing some of the information. We don't care about that. We just wanted to see what they are, not to actually find the final area. After we get through to a good stopping point, we can. All right, so that was all things difference of perfect squares. So you'll notice they all involved in one way or another a perfect square of sorts. I would just say be careful because there will be one on the test tomorrow where you'll need to remember to take out that greatest common factor first. But otherwise, the test looks very similar to this. So if you're not quite comfortable yet with it, talk to me before tomorrow and we can maybe look at a few more examples. Our next page, we're on a good roll here, so I want to try to get a little bit over halfway before we take a short break. The next one is solving quadratic equations by factoring. Now, I gave you some steps in an earlier lesson last week. I'm going to give you a very, very abbreviated version of those steps for solving quadratic equations. First one, set equal to 0. So everything needs to be on one side by itself. Step 2 is to factor. Now, Notice I'm not telling you how to factor. That could be greatest common factor. That could be the asterisk method. That could be grouping. That could be a difference of perfect squares. It really just depends on the problem itself. Third step is to set each factor equal to 0 separately. And that is thanks to the zero product property. And the fourth is to solve. Because at that point, you're going to have at least two equations. Solving each of them is going to give you typically your two solutions you're looking for. So again, this is extremely abbreviated. We spent a whole day on this process. If this is too abbreviated, I would suggest dig through your notes, take a look at the examples we did. I forget which day it was. I want to say it was last Wednesday. So 2 days ago, 2 lessons ago. And it describes it in a little bit more detail. And of course, we have the examples there that we did together as well. So this is just a very abbreviated form. So let's see it in action. Number 1, it is multiple choice. Don't let that distract you. And this one looks a little bit different than some of the others because right off the bat, what do we notice already?
They're in parentheses.
They're in parentheses. That's a little bit unique, but the fact that they're in parentheses, that tells me that they're already factored. Now, this would only be useful if it was already set equal to 0 as well, which it is. So it appears that this one's halfway solved already. So it's already been set equal to 0, and it appears to already have been factored, which means we actually skip ahead to step 3. And according to the zero product property, either n plus 4 would have to equal 0, or 3n minus 1 would have to equal 0. Now, we're going to take these two individual equations and we're going to solve them. Some of them involve a little bit more work than others. How would you solve the first one?
Minus 4.
Minus 4 from both sides. So we get n equals 0 minus 4 is negative 4. And how would you solve the second one?
Use the negative 1 first.
Yep, so add that 1 to both sides. I get 3n equals 0 plus 1, which is just 1. Divide both sides by that 3. I get n equals 1/3. So my answers are negative 4 and 1/3. The only option there would be C. Good. Now remember, this one was already halfway done for us. Already set equal to 0, already factored. Some of these next ones, we're going to have to do a little bit more work on our own. So let's take a look at this next one. Remember, running through our steps, first thing, I need it set equal to 0.
Yes.
Already done. Step 1 is done. That's convenient. Step 2 is to factor. So we go back into factoring mode. We've been doing this for a few pages now. Anytime we're factoring, what do we always check for first?
Greatest common factor.
Is there a greatest common factor here?
Yes.
What can we, well, 1, yes, but there's actually a larger one,
3.
a 3. Good job. We could take out a 3 from each of these 3 terms on the left. So setting that aside, before I divide, I should get,
Not an X too.
well, we could out of the first 2, but because this third term doesn't have an X, we can't take it out of all of them. So that would upset our problem. So dividing out of 3 here, I should get 5x squared minus 8x minus 4. Don't forget though, this is still all set equal to 0. That's important. We'll come back to it later. So off to the side here, I still need to try to factor it. So what's my A?
5, that's 5,
The 5. My B
-8,
is a -8, and the C
-4,
is a -4, because we're trying to factor this completely. So I'm thinking asterisk method here. We have the A, the B, and the C. So A times C on top, 5 times -4 will give me a -20. A on either side will give me 5s. B on the bottom, -8. So two factors that multiply to equal -20, but also add to equal -8.
2 and -10.
2 and -10. Let's do a quick check. 2 times -10 is -20. 2 plus -10 gives me that -8. So that sounds good. We have our two pairs now. Do either of them simplify?
yes.
Which one?
Yeah. 1 over -2 for the second.
On the right hand side there. So taking out a 5, you get 1 over -2. I think 5 over 2 is already as simplified as it can get. Bring back your variable, which in this case was an x. And then back to my work here. Now that it's factored, I have 3 times the binomial 5x plus 2 times the second binomial 1x minus 2. And this is still all set equal to 0. So it was already set equal to 0. We just finished factoring it. Step 3, set each of those factors equal to 0 to see what solutions you get. So either 3 equals 0, but can I throw that one out? Can 3 equal 0?
No,
No. So it was important for factoring, but it will not give us a solution. But we still have 5x plus 2 could equal 0, or x minus 2 could equal 0. How would you solve the 5x plus 2 equals 0?
move the 2.
Move the 2, subtract 2 from both sides. So 5x equals -2. Then what?
Minus, plus 2.
I'm not done solving the first one.
Divide by 5.
Divide both sides by 5. We get x equals -2/5. I'll go ahead and write that on my answer line here. How would you solve the second one?
Plus 2.
Plus 2. So I get x equals +2. That one's done. So it looks like my two solutions are -2/5 and +2. So some of them are going to require a little bit more work than others, but the goal is still the same. Set equal to 0, factor, set each equal to 0 independently, solve. Let's squeeze one more in, and I think that'll be a good point to take a short 5-minute break because I myself need to run to the restroom. Number 3 is a little bit different right off the bat. What do you hopefully notice? Well, I don't see one yet, but there's something even before all that, even before the factoring.
Move 12.
The +12. Why is that? What's our goal?
To make it equal 0.
Need it to equal 0. So I need to get this 12 out of the way first. So I'm going to subtract it from both sides. That removes it from the right. We do actually have a like term on the left to subtract it from. So it looks like I'm going to get x squared plus 5x minus 24 equals 0. So that's good news. So it's set equal to 0. Now I'm ready to factor. Is there a greatest common factor other than 1? No, that 1 at the front there really kind of traps us. So then we need to transition into the asterisk method, for which, what's my A?
1,
1. My B
5,
is 5, and my C
negative 24.
is negative 24. Dropping those values into my asterisk. And have A times C on top. 1 times negative 24 is negative 24. A on either side gives me 1s. B on the bottom is 5. Two factors of negative 24 that also add to equal 5.
Negative 3 times 8.
Negative 3 times 8. So negative 3 times 8 gives me negative 24. Negative 3 plus 8 gives me a positive 5. So we got it first shot. I don't think either of these simplify because of the 1's on top. So I'll bring back the variable, which is an x, and that should give me back here where I was working the two binomials, 1x minus 3 times 1x plus 8, still set equal to 0, but it's now factored. Step 3, thanks to the zero product property, tells me that either x minus 3 has to equal 0 or x plus 8 has to equal 0. How would you solve the first?
Plus 3.
Plus 3 to both sides. So I get x equals 0 plus 3, which is 3. How would you solve the second?
Minus 8.
Minus 8 from both sides. X equals 0, take away 8, which is negative 8. And it looks like I get the two solutions, 3 and negative 8.
I think your mic's off, Josh.
Shoot. Thanks, Tira. I'm glad you caught me before I went too far. So yeah, so Mike was off. Quick summary for the recording, because otherwise it just looks like I've lost my mind. First thing, as with any of these quadratic equations, we needed to set it equal to 0. So we subtracted the 16 over. Now remember, I just said factoring for step 2. So that could be anything, greatest common factors, grouping, asterisk method, or in this case, difference of perfect squares, that allows us to factor it, because our end goal really is to try to get it so that we have a product set equal to 0. And in this case, we have two binomials set equal to 0. Thanks to the zero product property, either 5x plus 4 has to equal 0, or 5x minus 4 has to equal 0. Oh gosh. So then I'm going to go through and solve these. What would you do to solve the first?
-4.
Minus 4 from both sides. So I got 5x equals a -4. And then what?
You divide by 5, which gives you -4/5.
Divide both sides by 5. You get -4/5 or -4/5. How would you solve the second one?
+4.
Add 4 to both sides. So on the right here, we're adding 4 to both sides. Gives me 5x equals +4. Divide both sides by 5. I get x equals +4/5. Those are still considered two separate answers. Yes, they're opposite, but that makes them unique. Okay. So again, those steps still hold true regardless of what the factoring looks like. But before you jump the gun, before you try to start factoring, make sure it's set equal to 0 first. Now, the last one for this page is one of those ones where it's already been solved, but it's been solved incorrectly. So we need to find the error and then also correct it so we can also list the correct solutions. So what I would suggest is we'll just check in with these steps periodically, but let's go with our instinct. Let's go through as if we were solving this ourselves. Right off the bat, though, if you're looking at this problem, what's my first concern? It's not equal to 0. So I should be able to move these two things at once. I would subtract the 3x from both sides. There is a like term on the left I can actually subtract it from. But I can simultaneously subtract the 8 from both sides because it too has a like term on the opposite side. That will remove everything from the right-hand side, which looks good. That does then give me x squared plus 10x minus 3x gives me 7x. 18 minus 8 gives me +10. Now set equal to 0. And I do believe their step 1 is the same. So their step 1 is correct. They got it set equal to 0. They don't exactly show how they moved those pieces, but the result is the same. After it's set equal to 0, next thing I need to do is I need to factor. Now, what do I always check for first? Greatest common factor, which I don't believe there is one. So then I switch gears here and I think, okay, maybe the asterisk method. And for that, what's my A? 1. What's my B? 7. And my C is 10. So setting up my asterisk. I have A times C on top. So 1 times 10 gives me 10. A on either side are 1s. B on the bottom is 7. So I'm looking for two factors of 10 that also add to equal 7.
2 times 5.
2 times 5. Do a quick mental check. 2 times 5 is positive 10. 2 plus 5 is positive 7. Sounds good. Do either of these pairs simplify? Nope. So they're good as is. So we'll still have one with the 2 and one with the 5. Bring back my variable x. I'm hearing that the second step is wrong. Let me write this out real quick. 1x plus 2 times 1x plus 5 equal to 0. Zoom back out to see theirs. Uh-oh, they have x minus 5 and x minus 2. Seems to me like that. It's not right. What do you suspect they did there? Or what? Why is it wrong?
Because it's negative, not positive.
Because the 5 and the 2s are negatives, not positives. And if we think about it, in our asterisk method, if we had made the 5 and the 2 negative, that would have given me a negative 7, where I wanted a positive 7. So we'll say real quick, in step 2, they choose the wrong signs when factoring. Now, let's not worry too much about the rest of their work, because as soon as you make a mistake, obviously that mistake then continues to carry through. But if we were finishing this one, if we were going to finish solving it, according to the zero product property, either x plus 2 has to equal 0, or so either x plus 2 has to equal 0, or x plus 5 has to equal 0. How would you solve the first? Minus 2 from both sides. So x equals negative 2. How would you solve the second one?
Minus 5.
Minus 5 from both sides. So x equals negative 5.
So they relatively got the correct answers. I just wanted to put their negatives.
Well, so the reason why they got positive answers and we got negatives is because the previous step, when we factored, we used positive values. They used negative values. So it's because of the switcheroo earlier on that their final answers were the opposite of ours. And that's because they used opposite factors than us in their step 2. So yes, close, we could say, but unfortunately not close enough.
Or
You're fine.
the song for the next thing is stuck in my head.
The song for the quadratic
Yeah,
formula.
the Pop Goes the Weasel song.
So I don't think I ever learned the song for it. So
My free algebra teacher played that the whole time we were learning that in high school. And that's how I know that equation is, because it's stuck to Pop Goes the Weasel in my head.
well, you're in luck. Everybody else, if you don't know that song, this is the formula. This is one of the many formulas you'll be provided. So again, we talked about last Thursday, whenever you're solving a quadratic equation and it happens to not factor, initially we were dead in the water, but thankfully there is a formula that allows us to kind of get over that hurdle. So still solving quadratic equations. And again, we like them in this particular format of descending order, ax squared plus bx plus c equals 0. And if they're in that, so set equal to 0, descending order, quadratic, all that, we then can use the formula that x equals negative b plus or minus the square root of b squared minus 4 times a times c that whole thing over 2a. So again, if you want to jot that down, we're going to use that 3 times here. But that would be something you would be provided on, say, the reference sheet for the test tomorrow. So don't panic and think, I have to memorize this. Really, I just want you to be comfortable using it. And another thing I'd point out is that because of the nature of these problems, we are going to have a point where we have to round. So if you could, as soon as you have to start rounding, just make sure you consistently round it to the nearest hundredth whenever needed. That's two digits after the decimal point. Now, similar to factoring, in order to use the quadratic formula, we still need it set equal to 0 because we're still kind of using the same A, B, and C we would be using in the asterisk method. So are we in luck on this first one?
Yes.
Absolutely. So this first one's already kind of set up in favor of it. So off to the side here, I'm going to list the information we need. What's our A?
1,
1. What's our B?
7,
7. And our C
-12.
is a -12. So jumping straight into our quadratic formula, our variable is an x this time. So I'll have x equals negative of b, which I replace with a 7. Remember, I like to wrap them in parentheses. That'll help me clean it up later. Plus or minus the square root of b, which is still that 7, squared, minus 4 times a, which is 1, times c, which is a -12, and then the entire thing over 2 times a, of course, replaced again with a 1. And I know I did this last week, but just for the sake of seeing it, anywhere we saw an a, we replaced it with a 1. Anywhere we saw a b, we replaced it exactly with a 7. And anywhere we saw a C, we put our -12. And just to kind of give you kind of a sneak peek into my method of grading these problems on the test tomorrow will be worth 4 points. You will get 2 of the 4 points simply by dropping the correct values in the correct spots. So even if you don't feel comfortable working all the way through this problem, you can still get half the credit simply by plugging them into the formula. Now, so in this next step, we go through and start to clean it up pretty quickly, addressing each set of parentheses as we go. So in my next step, I'll have x equals -7, which is just a -7, plus or minus the square root of 7 squared, which is 49. And then I have -4 times 1, which is -4. Take that -4, then multiply it with the -12, which gives me a positive 48. And then this whole thing is over 2 times 1, which is just 2. Already looking a lot nicer, a little bit cleaner. Still have those 2 pieces inside the square root that we can combine. That's going to help me here later on. So -7 plus or minus the square root of 49 plus 48, which gives me 97. Still all over 2. Don't lose any pieces because you don't want to write down the step in its entirety. Now, at this point, if I were trying to calculate the square root of 97, I would think, well, that's not on my list of perfect squares. This is going to be where my calculator is going to give me an approximation. So off to the side here, I need to know to the nearest hundredth what the square root of 97 is.
9.85.
9.85. And again, that's approximate, and that's according to my calculator. But what that allows me to do now is anywhere there's a square root of 97, I can replace it with the approximate value of 9.85. So now I'm at the situation where I can say that x is approximately -7 plus or minus 9.85, still all over 2. Notice the sign change. It's no longer an equal sign. It's a little approximation sign. Because as soon as you start rounding, you're no longer dealing with exact answers. You're dealing with close answers. Now, once you've done that approximation and you've reached this point, you are now ready to split at the plus or minus. So again, to draw your attention, that's right here. That's the only thing that should be different between our two equations. So either x is approximately -7 plus 9.85 all over 2, or x is approximately -7 minus 9.85 all over 2. Once they're split, you solve each of them individually in their entirety, all the way down till you get a final clean solution. So I'm going to start here on the left. -7 plus 9.85, I believe, is 2.85. Hopefully someone is checking me as we go. And if you divide that by 2, what do you get?
1.43.
1.43. Okay. Did you get the same, Leanna?
Yeah.
Okay. Moving on to the second one, x is approximately -7 minus 9.85, I believe gives us -16.85 over 2. And when you divide that by 2, I know it's negative. I'm guessing it's
-8.43.
-8.43. So like that, we get two solutions, 1.43 and -8.43. Took a bit of work. It took a lot of organization, but just like that, we solved the problem. Now, looking ahead to the second one, what's my immediate concern? I need to move the -2. It has to be set equal to 0 before I can apply the quadratic formula. Otherwise, I'll be using the wrong A, B, and C. So zooming in here, how would you move that -2?
Add it to the 21.
Yep, so add that 2 to both sides. So it's going to give me 8x squared minus 3x, -21 plus 2, I believe, gives us a -19. Set equal to 0, which I like to see. Because now that it's off to this, or set equal to 0, what's my A?
8.
8. What's my B?
-3.
-3. And my C
-19.
is a -19. And that C especially is where we would have had an issue if we had not first set it equal to 0. And it seems subtle. You think, oh, 1 out of 3 being wrong, that's not bad. Yep, it's very bad. So with those values, we're ready to plug into our quadratic formula yet again. So we're going to have x equals -b. So we'll have negative, and then the b is a -3, plus or minus the square root of b, which is still a -3, squared, minus 4 times a, which is 8, times C, which is a negative 19. This entire thing over 2 times A, which is 8. So again, there's half the credit simply by dropping them in to the appropriate locations. To get the other half of the credit, you got to see this thing through. So the next step would be cleaning up those parentheses one at a time. So I'll have negative 3, which is a positive 3, plus or minus the square root of negative 3 squared. That's negative 3 times negative 3, which is a positive 9. Then I may need to grab a calculator here. Negative 4 times 8 is a negative 32. And then the negative 32 times negative 19. I know it's positive. 608.
Let me recheck that.
Is that what you got, Tiara? Yep, she's nodding her head. So two people, odds are, unless we, by some circumstance, made the same mistakes, that's encouraging. The whole thing's over 2 times 8, which is now 16. We keep going. We still have some things we can combine inside the square root. So I'll have 3 plus or minus the square root of 617 when I add the 9 and the 608. Still over 16. Now we grab our calculator yet again, and we need that approximate value of 617.
24.84.
24.84. So anywhere now we see the square root of 617, we can replace it with 24.84. And this was all thanks to our calculator. So now we're saying that X is approximately 3 plus or minus 24.84 all over 16. And now that I've taken it this far, we're ready to split. So X is approximately 3 plus 24.84 over 16, or X is approximately 3 minus 24.84 divided by 16. So 3 plus 24.84 gives me 27.84. When you divide that by 16, what do you get?
1.74.
1.74. Someone else also want to confirm? Tara? Tara's got the thumbs up as well. Then on to the second one here. 3 minus 24.84 gives me a negative 21.84. Divide that by 16.
Negative 1.37.
Negative 1.37. Tara's nodding as well. Good. I like at least 2 students who are kind of checking themselves, bounce their answers off of each other, because odds are we'll catch it if we steer astray. So there's 2 of them. Again, very repetitive, so long as you're making sure that the conditions are met before you start using the quadratic formula. Moving on to our last one, a little bit different, but only a little. What's my first concern?
4x.
What about that 4x? Why don't I like it there? I need it to be equal to 0. So I would subtract that 4x from the right. Now, is there a like term from the left? No, there's no x term on the left. But here's the thing. I need to think ahead. I do want it in descending order. So will I want that minus 4x to be the first, second, or third term?
Second.
Second. So I'll kind of like squeeze it right here so I can mentally remember where I want it to go. It's gone from the right. That's what I also wanted to happen. But I should then be able to write this as x squared minus 4x minus 24 is equal to 0. I don't think I give myself as much space on this one. Let me see. Yep. We'll work with it. So with it set equal to 0, what's my A?
1,
A is 1. What's my B?
-4,
-4. And my C?
-24.
-24. Again, if you weren't paying attention when you were setting it equal to 0, and if you just kind of threw the terms wherever they were at, you would have your A, B, and C possibly scrambled up. And because they have to be dropped into particular spots in the quadratic formula, that's going to mess up your answer. But now that we have the right A, B, and C, we're ready to start dropping them in the quadratic formula. So I'm going to have negative of B, so negative of -4, plus or minus the square root of B, which is still -4 squared, minus 4 times A, which is 1, times C, which is a -24, that whole thing over 2 times A still being 1. Next, I'm going to go through and work on cleaning up my parentheses. -4 becomes a +4, plus or minus the square root of a -4 squared should give me a +16. Then I have -4 times 1, which is -4. Take that -4 times -24 should give me a +96. Which I'll go with until someone tells me otherwise.
No, it's on the back side.
Over 2 times 1, which is 2. Cleaning up a little further here. Inside the square root, 16 plus 96 gives me 112, I believe. And then at this point, we grab our calculator because I need to know approximately the square root of 112.
10.58.
10.58. Okay. So that means then that x is approximately 4 plus or minus 10.58 all over 2. And let me see how much space I have here. Not as much as I'd like. So I'm going to say we're going to split, but I'm going to take my split and bring it over here. I want to make sure I have plenty of space to see this written out. So x is either approximate to 4 plus 10.58 all over 2, or x is approximately 4 minus 10.58 over 2. It's a lengthy process, but it gets us there. So starting with the one on the left, 4 plus 10.58 is going to give me 14.58. And when I divide that by 2, what do I get?
7.29.
7.29. Moving over to the second one, 4 minus 10.58 is going to give me a negative 6.58. And when you divide that by 2,
-1.37.
oh, careful.
I got -3.29.
I think it's negative 3.29. Double check for me real quick, Tira. Did you get the negative 6.58 on top?
I think I was looking at the wrong problem. I got,
Oh, okay. But you found it then?
yes.
Okay, good. So we get the two answers, 7.29 and negative 3.29. So again, repetitive, but minor differences because you want to make sure that they're always set equal to 0 first. We're getting there, guys. Home stretch. So last page here, 2 questions, real world applications. So basically kind of taking a little bit of what we've been doing, throwing a story around it, and using our common sense to decide, okay, what is my final solution and is it reasonable for what's being described here? So we're going to work these 2 out, excuse me, one at a time. First one says that a frog jumps from land to a lily pad on a pond. His path of travel is modeled by the function h equals 2x squared minus 5x minus 52. And this is where h is the frog's height above the water and x is the distance from the shoreline in feet. So the question, how far away is the lily pad from the shore? Well, if you think about it, the moment the frog lands on the lily pad, his distance from the shoreline is the same distance as the lily pads from the shoreline. So we're going to use the frog's path of travel, the function we've been given, to help us out here. So how far away is basically asking us, what is x? Now, from the story, let's think about it. If we're looking for x, we had better know something about h. If you think about it, h is the frog's height above the water. The moment he lands on a lily pad, how high above the water is he?
0.
0, because if you think about a lily pad, the lily pad is on the water. Therefore, the frog itself is on the water. Now, some would argue, well, technically the thickness of the lily pad would be, we're not worrying that too much about that detail. So we're going to say that h equals 0. And that's because the frog has landed on the lily pad, therefore is on the water. So what that allows me to do is to take this equation, this function, and say that 0 equals 2x squared minus 5x minus 52. And if you think about it, it's now quadratic and it's set equal to 0, which is exactly what I like to see. So we actually have 2 options here. We can try to factor this one to solve, which I will tell you it does factor. Or if you absolutely love the quadratic formula will give you the same 2 answers. Now, I personally like to factor if it does factor. So what should I check for first?
Greatest common factor.
Is there a greatest common factor? No, because 2 and 5 are both prime numbers. So the only factor they share is 1. Excuse me. So then I think, okay, let me try the asterisk method. What's my A?
2.
My B
-5.
is -5, and my C
-50.
is -52. So then I set up my asterisk. Doesn't have to be anything too fancy, just enough to accomplish the task. Okay, so setting up the asterisk here.
I got a question, Josh.
Yeah, sure.
How would you know to just use that instead of what we were just doing with like the formula?
The quadratic formula,
Mhm.
I wouldn't know until I tried to first start factoring it. So I know that this one factors because obviously I wrote it. But if I didn't know, what I personally would do is I would try this, set up the asterisk, try to factor it. And if it comes to find out, if you realize that it's not going to factor, or you're just having an off day on factoring, you can actually go back, because what's nice is the A, B, and C you're using for factoring are the same A, B, and C you would use in the quadratic formula. So you could then switch very easily over to the quadratic formula and pick it up from there. Now, if you like the quadratic formula, you can use the quadratic formula every single time it's a quadratic equation, because it will work whether it factors or not. So the quadratic formula always works if there's a real solution. Factoring, well, obviously it has to factor in order for it to work. So I don't know until I try factoring it first.
Okay, cool. Thank you.
You're welcome. So here I've got A times C on top, 2 times a negative 52, which will give me a negative 104. A on either side are 2's. B on the bottom is negative 5. So I want two numbers that multiply to equal negative 104, but add to equal negative 5. I grumble a little bit because 104 is not on that factor pair list. So I may need to make my own, unless you can think of one off the top of your head. So if I was in this situation, I'd say, okay, 104. 1 times 104, I know that one works. 104 divided by 2, I get 2 times 52. Divided by 3, nope. Divided by 4, I get 4 times 26. It doesn't divide by 5, I try 6, nope. 7, nope. 8, yep. 8 times 13. 9, nope. 10, nope. 11, nope. 12, nope. 13, already on my list. So I have my factor pairs here. Negative 8 and 13. Let's check. Negative 8 times 13 would give me a negative 104. What's negative 8 plus 13? Positive 5. No panic. That just tells me that I put the negative sign on the wrong value. So the 13 should be negative instead of the 8. Now, do either of these pairs simplify?
Yes,
Which one?
the one that you just taught, the 2 and the 8.
The 2 and the 8, divide out a 2 from each, you get 1 over 4. The 2 over negative 13 is already simplified. So remember, we're still in equation mode. So those binomials are helping me solve this equation. So this equation now can be written as 0 equals, bring back my variable x, 1x plus 4 times the binomial 2x minus 13. Well, now that it's factored, thanks to the zero product property, I know that either x plus 4 has to equal 0, or 2x minus 13 has to equal 0. How would you solve that first equation?
Negative 4.
Subtract the 4 from both sides. So I get x equals negative 4. What about the second one?
You look at 13.
So add 13 to both sides. I get 2x equals 13. Then what?
Divide by the 2.
Divide both sides by 2. I get x equals, well, I'm going to go ahead and divide this one because it divides kind of okay. 6.5. Now, we can't forget x actually represents something here. X is the distance from the shoreline in feet. Which of these kind of hurts my brain?
The negative?
The negative, because in our mind, distance, hopefully, cannot be negative. At least not the way we understand it, or we do it day to day. And I will tell you, there is scenarios out there. There are scenarios out there. Oof, my wife would be so disappointed in my grammar. There are scenarios out there where the negative distance actually has some value to it. In this case, again, we won't dig into it. The -4 is actually telling me how many feet inland the frog is before he jumps. He's 4 feet inland before his jump. He is 6.5 feet from the shoreline after he lands his jump. But again, don't worry too much about that. We know that when the frog lands on the lily pad, therefore is on the water, he is 6.5 feet from the shoreline, which is quite a distance. There we have it. Now, this last one, similar to the last test, just because it feels right. The last one is going to be worth bonus. If you can do the counterpart on the test tomorrow, the very, very last question at the very, very last page, you can earn a couple bonus points. And on a test, that's pretty significant. Because this one does require a little bit more work, because you actually have to develop the equation yourself before you can then turn around and solve it. So it takes some work. So the scenario says that the length of a sports field is 10 feet shorter than twice the width. That seems important. It's telling me something about the length, and it happens to be in terms of the width. We'll come back to that in just a moment. The entire field covers an area, that sounds significant, of 1,500 square feet. The question is, what are the dimensions of the sports field? Well, unless it's baseball, most sports fields are what shape?
Rectangles?
Rectangular. So I'm thinking here, area of a rectangle equals the length times its width. Now, in our case, I'm going to abbreviate this down a little bit. A equals L times W. We need to try to figure out what information we have for that formula already. What do we know right off the bat?
Area equals 1,500 square feet.
Area is 1,500 square feet. So we have a value for area. Do I know anything about the length or the width? Not specifically, but that first statement up there said that the length of the sports field is 10 feet shorter than twice the width. Well, to get 10 feet shorter, you would subtract 10. And in this case, we're subtracting 10 from twice the width, which would be 2W. So that statement up there, let me actually write it above it. Length is 2W minus 10. The length is 10 feet shorter than twice the width. Gives me that statement. So over here in my formula, I'm going to replace the L with 2W minus 10. And then unfortunately, I know absolutely nothing about the width. I know how the length compares to the width, but I don't know anything about the width itself. So good news is technically we have our equation. Now we're going to go through some changes on our equation here in just a moment. But technically this would meet the requirement of the equation because it relates the information we're given, and this is the equation we're going to use to solve it. Now, this whole test really is a lot about quadratics and things like that. And right now it doesn't look quadratic, but hopefully our brain is drawing our attention to what?
Equal to 0.
Well, it's not equal to 0. We like that to happen. But even before that, what should usually catch our eye very early? The parentheses. And in this case, the parentheses are going to have me distribute what?
The W.
The W. So in distributing the W, I would get 2W squared minus 10W. And at that point, I'm thinking, okay, well, now it looks quadratic. Well, if I'm solving the quadratic equation, Leanna, you said it earlier, it needs to be equal to 0. What can we move here? The 1,500. I'm going to subtract that from both sides. Now, there isn't a like term on the right-hand side, so it's just going to kind of get attached there at the end. But I'll get 0 equals 2W squared minus 10W minus 1,500. And now it's starting to feel like some of the problems we did earlier. We set the quadratic equation equal to 0. Next thing I want to do is factor. Anytime we're factoring, what do we check for first? I think there is one. They're all even, so I can divide them all by 2. So I'll have 0 equals 2, and then in parentheses, we'll have 1W squared minus 5W minus, what's that? 750. Still factoring. What's my A? 1. What's my B?
-5.
-5. And my C?
-7.
-750. Oof. Hopefully this one works out nicely. Going into asterisk mode. A times C on top, 1 times -750 is -750. A on either side are 1s. B on the bottom, -5. I would suggest sticking with multiples of 5 because I think, if I recall, what's 750 divided by 25?
6.
25 times 6? Doesn't sound right.
Yeah, it's all right. 25 times 6 is 450.
750. Do 750 divided by 25.
30.
What's the difference of 25 and 30?
5.
Now, which of these would have to be negative?
30.
The 30. That's the only way to get the -5 on the bottom. Now, do either of these simplify?
No.
Nope. That one on top kind of saves me from having to simplify any further. So when I bring back the variable, this time a W, I'm going to get the 2 binomials. Don't lose the 2 yet. But 1W plus 25 and 1W minus 30. Now, thanks to the 0 product property, either 2 has to equal 0, which we know cannot happen, or W plus 25 has to equal 0, or W minus 30 has to equal 0. Now, how would you solve that second one? Well, the second, 2 equals 0 is the first one. Second, I'd have to subtract the 25 from both sides. So that gives me W equals negative 25. What about the last one? Add 30 to both sides. We get W equals 30. But what does W represent? Our width. Which of them does not make sense?
Negative 30 or negative 25.
Negative 25. So our width cannot be negative. So although it works for the equation itself, it doesn't fit the context of the story. So in this case, my width must be 30 feet. What do I still need? My length. What do I know about the length? I had it all the way back at the beginning.
It's 10 feet shorter and twice the width.
Is 10 feet shorter than twice the width. So earlier on, we said that the length is 10 feet shorter than twice the width. Well, now that I know what the width is, I drop it in. 2 times 30 is 60. 60 minus 10 is 50. Now, like I said, that one will be worth extra credit on the test because it was very involved. You had to work through the problem to write the equation, and then you had to go through the whole process of solving the equation. But if you can do it, give it a shot. Some bonus points would be helpful there.